I'm recording now. The time is 5 past 5. Let's start with our lessons. Good afternoon, everybody. Thank you for joining. All right, as you all know, my name is Mr. Mapeza, and then we're doing our first lesson of 2021. I welcome everybody to Geography 2021, and I hope we're gonna get distinctions. Okay, I know we're gonna get distinctions like we did last year, and everything will be fine. Right. This module has been trimmed. Wait a minute. Sorry for that. Right, this module has been trimmed because of COVID-19. We started the year 2 weeks later. So some of the topics have been removed, but I sent you the ATP for what you guys are going to be doing in term 1, 2, 3, and 4. Right, so let's get straight into it. Right, last week we had our first post, which was lesson 3. So lesson 3 was your first lesson, and then I posted it, and then I was supposed to do a follow up with a live lesson, which is what I'm doing now. Right, as you can see on lesson 3, there it says transfer of energy and energy balance, role of ocean currents and wind. Okay, if you look at your ATP, it says um, global air circulation, world pressure belts, tricellular circulation, the relationship between air temperature, air pressure, and wind. Okay, so it's at the bottom. It's what we're starting with now. Right, the sun. Listen, those are the words that are included in this topic now. Winds and ocean currents. Okay, so everybody understands ocean currents, ne? So basically, when we're talking about ocean currents, we're talking about how the water moves and transfers heat across the world. So, for example, if the water is moving from the equator, it means that it is carrying a warm current. Ne? We say a warm current because the water is moving in currents, and then it is warm because it's coming from the equator. And then winds as well are also part of this particular movement of energy. The wind, which is blown from the equator to the north and south poles, is also responsible for carrying and transferring heat across the world. Right. Transfer excess energy from the equatorial region to the polar region. So if we're talking about the equatorial region, we're talking about the equator, and polar region, we're talking about the North Pole and the South Pole. Oceans transfer 30% of excess energy. All right, so which means 30% of the heat that is transferred around the world is carried by the ocean. Surface wind transfer energy, and convection transfers energy. Humans are interfering with energy balance. Okay, all right, let's look at the presentation. Three-quarters of the Earth's surface is covered by the oceans. These oceans receive almost 80% of the insulations reaching the Earth. The exchange of heat energy drives the global wind circulation system, which in turn powers the circulation of the oceans. Okay, so if the ocean is moving from the equator going to the north or south pole, it means that it's transferring energy from a region of from a warm region or hot region to a relatively cool or colder region in the north or the south. Right. Let's leave the oceans. The winds, in turn, push the waters of the ocean in set directions. Okay, so you can't have a current if you don't have wind. So the wind is also responsible for moving the ocean currents along their path that they take in transferring heat. Right, heat transfer in ocean currents. Right, the end result of heat transfer through the process of radiation, conduction, and convection. We did this in grade 10. Ne? Radiation, conduction, and convection is how heat is transferred. Ne? Right, in the oceans and atmosphere is a complicated balance of the input of energy from the sun with outputs of energy from the earth, right? So if we have incoming solar radiation from the sun, which is the main source of energy, which is transferred through radiation, shortwave and long wave radiation onto the earth, and then we have terrestrial radiation, which is happening through conduction as the earth gives off that heat that it has collected from the sun through incoming solar radiation. And then we have the transfer of heat from the earth to the ocean, which in turn moves from the equatorial region, which is the hottest, to the polar regions in the north and the south. Okay, does it make sense? Right. Without this balance, the Earth will simply become too hot for life on Earth. So this means that as the heat is transferred from the equator, it also needs cooling from the polar regions. So this means the water which is moved from the equator carrying warm currents or hot currents to the North Pole and the South Pole, in turn comes back to the equator to cool the temperatures in the equator as cold currents are mixed with hot currents at the equator, and then we have a balance on Earth. Okay. Currents are warm or cold depending on whether they originate from the polar regions or the equatorial regions. Warm currents transfer heat away from the equatorial regions towards the polar regions. Cold currents move cold water towards the equatorial regions. Currents make the heat imbalance to be even. Okay, so if we say heat imbalance, this means that at the equator, we have extreme temperatures, and at the poles, we have low temperatures. So these ocean currents and winds make sure that the temperatures are balanced, and then the imbalance is even. Okay, all right, let's look at trade winds. Right, as you can see here, we have a red line, which is the equator, and then we have warm air, and then we have warm air, and then we have the clouds, and then we have solar energy. So this means that the air which is blown, the trade winds which are blown from the South Pole and the North Pole, go to the equator and then they pick up energy and then they travel back to the North and the South Pole, which brings a balance to, excuse me, the temperatures in both areas. Right. Global air circulation patterns and ocean currents. Right. So if you look at the map there, at the center, we have the red lines, and at the south, we have the blue lines, and at the north, we also have the blue lines, which means that the currents in the oceans are carrying the hot water towards the north and the south, and the currents at the south are carrying water towards the north, which is the equator, and then the currents at the north are carrying cold currents towards the south, which is the equator. Hence, we have a balance in a temperature in all the three areas. Okay, that was your lesson 3, your introduction. All right. So the activities you're supposed to do are from the textbook. Um, we'll talk about that now. All right. Let's move on to lesson 4. Lesson 4. Before we go to the textbook, let's talk about lesson 4. All right. Lesson 4. World pressure patterns. Okay. So as the waters and the winds are moving up and down, changing directions and pushing a heat from the north to the south to the north, from the equator to the North Pole and the South Pole, we have what we call pressure patterns. Okay, reasons for horizontal variation in pressure patterns. Okay, atmospheric pressure, the force per unit area exerted per unit area by the weight of a column of air above the surface, relationship between the temperature and wind. Right, A, when air is warm, it expands, density decreases. Therefore, air will have less weight and its pressure will be low. Again, you've seen that if the air is warm, it will rise again. A good example will be your boiling water in a kettle. When you boil the water, and then we have that evaporation taking place, that means that steam that is coming from the water that you boiled is warm, hence it will rise again. Right? When air is cold, it contracts, density increases, air will have more weight, and its pressure will be high. Basically, let's talk about, okay, let's give an example of water. When the water is cold, it becomes dense, and then it cannot rise. Ne? All right, that makes sense. Which hence we haven't got rain in winter because the air does not rise. It is dense because of the temperature. All right. Relationship between vertical air movement and pressure. When when air rises above the surface, the pressure at the surface will be low. When air subsides over a surface, the pressure at the surface will be high. Okay, we just spoke about that now. Right, what are pressure belts? Polar high pressure, mid latitude LP, equatorial, subtropic HP. Right, pressure belts are the lines that you see on a map that are connecting places of the same pressure. Okay, right. Okay, I'm not gonna read that. Okay, let's go to the textbook and then I explain clearly. All right, stop share textbook. Share. Right, now that we've spoken about ocean currents and air, right, we're going to move on to what we call global air circulation before we go back to ocean currents. So we're going to split these two, what do you call it, conductors of energy in the world, and then we'll look at each one individually, and then we'll see how it works. Right, global air circulation. Global air circulation is a response to unequal heating of the atmosphere. So basically, what we're talking about here is how the air circulates around the globe, transferring heat from the north to the equator to the south. Okay, right. Winds blow different distances over the earth. Some travel thousands of kilometers moving air right across the globe. This large scale circulation of air is the global circulation of the atmosphere. This unit will pay attention to the global circulation, and smaller scale circulations will be discussed later in this chapter. Right, global circulation of the atmosphere, large scale circulation of air across the globe, unicellular model of global air circulation, model of global air circulation featuring one cell of circulation in each hemisphere. Okay, again, we have two hemispheres, ne? And then in this case, we're going to talk about the tricellular air movement, where we have three cells that distribute air across the globe. Right, the unicellular model of global circulation. In its simplest form, the global circulation of the atmosphere would transfer heat from low latitudes to high latitudes in huge convectional cells, one in each hemisphere. Figure 2.15, as in figure 2.15. Because there is one cell of circulation in each hemisphere, this model is called one cell model or unicellular model of global air circulation. In this model, warm air rises at the equator and moves towards the poles. At the poles, the air becomes colder and sinks. The cold air travels back to the equator, completing the convection system. Okay, let's see how it works. Right, so we have one cell here, one cell there, and one cell there. Right, so this cell in the North Pole will be cold, this cell in the equator will be warm, and then the other cell at the South Pole will be cold. Hence is the unicellular model of global air circulation. So the air will move out in its warm state at the equator, and then it's distributed either south or north to the North Pole or the South Pole. And then when it gets there, because the temperatures are low, as you can see, the arrows are red here at the equator. It moves there, it becomes blue, and then it pushes down on Earth in its cold state, moving down to the equator where it picks up temperature, goes out again and goes up. The same thing happens with the South Pole. The air moves out as warm air, goes down, pushes in as cold air because it's dense, it can't rise, goes closer to the surface, and then it moves up to the equator where it picks up heat, and then it is pushed out either going north or south. Okay, right. To ascend is to move upwards, to subside is to move downwards, to converge is to move towards the same place, to diverge, move away from one place in different directions. Okay, vertical and horizontal air movement. Right, so vertically or upwards or downwards away from and towards the surface. I just spoke about this now. So when air moves upwards, we say it is rising or ascending. When it moves downwards, we say it sinks or descends or it subsides. Okay, that is vertically. Horizontally or parallel to the surface of the Earth, look at figure 2.15. This is the one. There you go. We will say, right, which shows the upper air moves horizontally in the upper atmosphere from the equator. Okay, let's make sense. All right, let's move on. Right, figure 2.16, links between horizontal and vertical air movement, surface convergence, and ascending air. Okay, right, there we have the arrows, surface convergence, ascending air, it's got temperature, moves up, becomes cool, and then it diverges. That means it moves further apart from each other, and then it goes around and then it comes back to converge at the surface, and then it moves up again. So it's moving in a circular motion as it goes around the world. The same thing happens there, it moves around, but this time it's going down in a horizontal form. Right. World pressure patterns, atmospheric pressure. Have we done this one already? All right. Let me stop there. Let's go back to the notes. Where is the note? Right, that was lesson 3. Ne? Let's move on to lesson 4 before I explain that stuff there. Right, lesson 4, world pressure patterns. Okay, just do this one. Oh yeah, pressure belts. The temperature difference cause different pressure regions around the world. The world consists of both high pressure regions and low pressure regions. In the cold regions, world has high pressure. In hot, warm regions, the world has low pressure. So basically, if we're talking about low pressure regions, we're talking about the low pressure regions, we're talking about the equator where the temperature is high, and high pressure regions, we're talking about the north and south pole where the temperatures are cold. Okay. Overall, the Earth consists of four pressure regions, belts. These regions are clearly illustrated in Figure 1. There's Figure 1 there. And then these regions, okay, 0 degrees line of latitude, which is the equator, is low pressure belt because the temperatures are high. 30-degree line of latitude in both north and south hemisphere is subtropical high pressure because it's close to the equator. And then subpolar 60 degrees and 90 degrees are at the poles where the temperatures are low. So you guys are supposed to know where these pressure belts are found and how it works. So you go to your textbook and then you will find page 97 where you have world pressure patterns there. Ne? And then remember we said the equator has low pressure because the temperature is high, and the poles have high pressure because the temperatures are low. All right. All right, horizontal variations. All right, let's talk about the relationship between vertical air movement pressure pressure. Ne? Right. So we're talking about the three cells. The three cells that you have the Ferrel, ne? You have the Hartley, and the polar. Okay, so it's polar, Hartley, and Ferrel. Those are the three cells you have. So the Hartley cell is found at the equator there, which means it's generating warm air both north and south. And then the ferrule is found in between at 60 degrees north and south, whereby it's distributing air, or it's mixing air, which is warm and cold as it moves towards the polar cell, which is found in the north and south. So the three pressure cells that you have are the Hartley, Ferrel, and polar. In a test, you're supposed to identify where you find the Hartley cell, the Ferrel cell, and the polar cell. So which means the Hartley cell is at the equator, the Ferrel cell is just above it, and the polar cell is found at the North Pole and the South Pole. Okay, right. I haven't got much time left, so I'm gonna ask people to ask questions about anything you don't understand, and then we can discuss that before the end of the lesson. So in this particular lesson, we spoke about global air circulation, pressure belts, and the tricellular circulation. Okay, then tomorrow we're going to talk about the relationship between air temperature and pressure and wind. Okay, can I have questions before the end of the lesson? Right, so I take it everybody understood what happened. Everybody understood what I spoke about. All right. If there are no questions, it's fine. Let's go back to the textbook and then we talk about activities. Let's see. So, seeing that we started at lesson 3, your first activity will be activity 6. Let me see. Let me see if it's correct. All right, let's start at activity 1 then. Your first activity will be activity 1. No, you can't do that one. Copy figure 2.15, label all places where there is convergence. Okay, yeah, we can do activity 1. So your first activity is activity 1 on page 96. You're supposed to do that today, and then we'll mark it tomorrow. And then your second activity is activity 2 on page 98. So you do activity 1 and 2, and then we'll mark both of them on Wednesday. And then I'll give you the third activity on Wednesday and Thursday. Remember, on Friday, we don't do activities again because we're actually trying to wind down and reflect on what we've done during the week. And then we have a lesson on Friday whereby we just ask questions and then we revise the work that we've done throughout the week. So, are there any questions, or you guys are good so that we're on the same page? All right, guys. If there are no questions, I'm gonna end the meeting and then I'll send another invite for tomorrow. Okay. Please, if you have any questions, you can send a message to me on my phone, and then we can discuss what you don't understand, and then I can see where I can help you. All right. Thank you for joining. I will see you guys tomorrow.